Got two slides of the general stochastic kinetic models that we'll skip through. But throughout this talk, I'm going to be talking about essentially chemical master equations, stochastic kinetic models, that sort of stuff. But anytime I say the word model, it could be anything we actually want. We're talking about these optimal designs. So we tend to have S species, R reactions. We've got the usual reaction representation here, things on the left are reactants, things on the right are products. We have some stochastic rate constants that we're interested in estimating. Okay, so we might know some of them. We might have some vague knowledge about some of the other ones, and we might have no idea about a bunch. Okay, and those are things we're interested in estimating. Okay. We've got some hazards, so how quickly does this reaction occur? This will depend on the species, it will depend on the parameter. And then we can assume mass action kinetics, but we don't have to. Okay, we can assume anything we want. So quite a generic framework. And so here's the classical law to Volterra, and we've got two species here. This is a single stochastic simulation, and again we can simulate this multiple times and we can get different realizations, and then we can have the average realization going through the middle as well. And there's varieties of ways of simulating these things, and we've had lots of talks on how to simulate these models. And my favourite, would you believe, is the Gillespie algorithm. And there's a whole bunch of undergraduates at Newcastle who believe I wrote this algorithm. I haven't had the heart to tell them otherwise. So they go out to the world and they were taught by the world famous Gillespie. But yeah, you know, it's fairly straightforward. So we've got a model and we can simulate from it. And we're just assuming we can simulate from it without too much difficulty. The motivation for this work came about because of this model. So this is a model that we've been looking at for the last few years. And we've had a PhD student who's just graduated a year ago who was doing parameter inference for this model. Okay? And it was based on these things, polyQ proteins. And they're relatively nasty because essentially they gather together and they give you not nice diseases, you know, so Huntington's disease. Okay? So this model here, the circles are species, the lines are trying to represent the interactions between the species, and this model is trying to capture the aggregation of polyQ proteins over time. Okay? So as this model proceeded through time, you got more and more of these clumps, these aggregated proteins, and at some point the cell died. Okay? And it's a stochastic version. There's about 33 reactions and there's 11 species. Some of the reactions are sort of, I suppose, almost pretend. So we've got polyQ1 going to polyQ2 to going to polyQ3, 4, and 5, and it's trying to get this idea of aggregation going on. Okay. There's 11 unknown rates. There's also all the different species, all have unknown initial conditions, and it's a bit of a mess. And the data that we got was proportion of cell death over time. And initially we had those four numbers. So, you know, the biologist had those four numbers and said, we want to infer some parameters. So, yeah, good luck with that.
Colin, can I ask something? So that assumes that you know the rest of, so there are like 33 reactions, you know 22 reaction rates, and you don't know 11?
So for here, we made some assumptions. So going from polyQ 1 to 2, 2 to 3 is the same.
Okay.
And proteins die at the same level. You know,
so you add stuff together.
We added stuff together and we tried to sort of anything that we could possibly say they're the same. We went for they're the same. Yeah.
So what is the role of the polyQ proteins? Is it that they ultimately lead to cell death?
Yeah.
Or?
Yeah, they lump together and lead to cell death.
Okay.
And in humans, they lead to not nice diseases, which leads to our death. So these four numbers was the initial data set that we got, and they were the proportion of cell death over time. So essentially what that meant was, if we simulated this model 1,000 times, we then get a proportion of cells that die. And would you believe you can't even do very much with those four numbers? What's even more interesting is proportion of cell death. Well, proportions tend to increase. You know, you've got 100 cells, you're going to get more things die, you know, nothing's going to come back to life. But that goes down, you know, so we've got noise on the measurements. So not only do we have lousy measurements, not only do we have few of these measurements, we've also got them with noise. It turned out it wasn't quite so bad, you know, so we managed to get when we sort of interrogated the scientists a bit more, it turned out that they had some replicates. It also turned out they had different scenarios of this model. So they might have knocked out one of these proteins at the top, ran the experiment again, and they got different proportions. And so we got, this was sort of the data that we had. And they go for different scenario types, so they're knocking out different proteins, different replicates. And my PhD student spent, well, 3 or 4 years of her life analysing this bunch of numbers. And you could do some parameter inference, okay? Parameter inference for this was hard, right? So some parameters you learn absolutely nothing at all. So the histograms are the posteriors, the red lines are the priors, and would you believe you learn nothing at all about that? Other times you learn something, we're narrowing it down. So it's a bit of a mixed bag. Okay? When we were doing this, we all sort of thought of, well, if only we had more time points, right? If we just sort of filled in the blanks with more information, parameter inference would be a lot better. That's intuitive, more data, better parameter inference. And it was towards the end of this project that it suddenly dawned on us that actually, if we had more observations here, it didn't really make the parameter inference much easier. It didn't really change it at all. And essentially the intuition that took us 4 years to get to was if you picture cell death, right, it's going to be a logistic curve. So it's going along at 0, then increasing, and then everything dies. If you've got 2 observations in that line, how many points does it take to fit a straight line? 2. So actually to estimate, if you wanted to estimate a logistic curve, you only need a handful of measurements in that logistic curve and you've pretty much got all the information. Okay? What we needed was different types of data, not just more observations. Another example that I've been working on for a few years is to do with cotton aphids, and so you've got a cotton plant and aphids essentially spoil the plant. Okay? Leaves curl and pucker, plants die, cotton gets messed up, and cotton aphids are a nasty little pest and they start to develop resistance to lots of the chemicals. And essentially it's costing someone money, right? Someone's interested in this because it costs money. Okay? And again, there's a simple, this one here, the stochastic kinetic model behind it is a lot more straightforward, sort of a lot of Volterra-like. And this was the data that we had, okay? And each of these points is an observation, and then each of these squares is a different treatment combination, okay? So going along down the bottom, we've got different fields with different amounts of water. So we've got a field up here that's got low water, medium amount of water, high water, and then going along the top, they varied the nitrogen. So it's a classic two-way ANOVA table design, two-factor design. And in each block, they had different observations. And whenever I think,
What is the difference of the colors? Why is red, blue?
Oh, they're just different replicates. So they've had 3 fields with 0 nitrogen.
Okay.
And whenever I think I hate my job, I think at least I'm not going around counting aphids on a field. It's 2,000s of the silly things. So imagine standing at a plant trying to count to 2,000. So there's also probably a bit of error on these numbers, I suspect. Doesn't count them exactly. But again, they're interested in, well, we've got this data, can we see how it affects the underlying birth rate and the underlying death rate of the aphids? And the way this experiment was designed was essentially that they're taken every week, which is sensible. Every Monday, off they go to the field and they count. And so, in both of these scenarios that we've looked at, we've had the data and tried to do parameter inference. But the obvious question is, well, if I was to redo this experiment, would I put those observations there? Would I have them every single week? Or would I have something else? For this, would I have them every 12 hours? If I wanted other types of data, what should it be? How do you make that, how do you make that decision? So, this is essentially an optimal design, right? We've got an experiment, and we can choose some things. What should we choose? How should we choose it? What ideas? So suppose we want to observe the process at k time points. Right? Let's make k1. Okay. So what's going on here? So we're allowed 1 time point. So we've got 1 here, that's time 10, 1 here, time 10, 20, 1 here, time 30. So if I observed that point here, that was the only thing I observed, this would be the posterior for the parameter I'll get for this particular model. Okay? If I only observed this point here, that would be the posterior I'll get here. If I only observe this blue point, that would be the posterior. Now we're just sort of pretending that getting the posterior is dead easy and we don't need to worry about that, but just go bear with me. Okay.
What was the value of theta in reality?
Oh, it'll be around about point, I think it's 0.21 or 2. But of course, this is a single stochastic realization. Right? If we simulated this model again, we get a slightly different line, and we've got a slightly different line, and so we get different posteriors for all these points. Right? Still the same model, it's still the same parameters, we just got a different posterior. And we can simulate the model for a third time, and we get another posterior for all these things. And so if I was to ask you, well, which time point would you like to observe the model at? Do you want to observe the model at time 10, time 20, or time 30? And sort of what you could think about intuitively doing would be go, well, this is what's happened when we've done it 3 times. And if we can sort of get almost an average accuracy, that would be a good idea. Perhaps we could get the mean squared error for each of these 3 curves and take the average. Or work out the posterior variance for each of these 3 posteriors, work out the average. And so we've now got a measure of accuracy at time 10, measure of accuracy at time 20, measure of accuracy at time 30. And then you can choose that, whichever one minimised the thing you wanted. And that's exactly what we're going to do. Right? That's this idea of optimal design. Of course, in this one toy example, we simulated the model 3 times, and then we performed parameter inference 9 times. Right? Remember, parameter inference is painful. Right? That's not nice. People give entire talks on that. My students spent their entire PhD doing it for 1, never mind 9. Right? So that's, that's not nice. So, some notation. So we're going to consider T time point designs. So we're going to get to choose capital T time points. Okay. The stochastic model is always going to have a parameter set theta, right? And we might have vague prior on some of those parameters. We might know them very well on others. We can have whatever we want. And then we're going to, the data is always going to be y. Okay, so my notation is always going to be data is y. This is a bit of an odd case, right? Because we don't actually have any data, right? Here, these curves are data, but I simulated them, so it's a bit of a sort of a pretend data set because I just simulated each value. I've not actually got measurements at this point, I've just got simulations. So here, y is going to be my simulations of my data. Okay? And what we're going to do is we're going to say, well, how do I pick the best design? Should I pick time 10, time 20, or time 30? Well, I'm going to try and sort of rank or work out the merit of a particular design using a utility function. Okay? And a utility function is going to be a function of d, where I observed. It's going to be a function of y, the stochastic simulation, and it's going to be a function of theta. Well, it can be a function of theta as well. If you're doing something like the posterior variance, then the utility function is just a function of d and y. Okay? So you might have a utility function that depends on theta if it was something that you could change. So for example, theta could relate to the voltage you're doing in the experiment, and you might want to penalise high levels of voltage. It's something you can control. That'd be the idea. Okay? So for the rest of this talk, my utility function is going to be the generalised precision of the posterior. Okay? So I've got all these posteriors. I work out the variance, or 1 over the variance for each of these posteriors. That's my utility function. I want to get a design that minimises the variance of these posteriors. I could have anything else I want, right? Whatever you want. The mean squared error. Yeah.
So in the language of the utility function, that's the thing that you want to maximize.
Yes.
But I mean, can I ask a naive question? I mean, posterior variance is not necessarily. I mean, what if you're getting the mode completely wrong and you kind of, I mean,
We can make that utility function. Utility function is just a. It depends how Bayesian you are. So you're Bayesian, you've got your data, you've got the posterior. That is the answer. It doesn't matter the true values. It's just what you've got.
okay.
But some people use mean squared error. You know what theta, the true value of theta is. You subtract it from your estimate. You square it.
I'm kind of thinking in the situation that you kind of have got your model kind of completely wrong.
Yeah.
So that, I mean,
Yeah.
Okay.
Yeah, but you can make this as complicated. You could include money into this. So how many design points? the more design points you've got, the better it's going to be. But more design points cost money, so this could easily include some idea of the larger the D, the more it's going to cost. Okay?
But what's the idea? Is it like roughly you're going to optimize the identifiability of the parameter by reducing the parameters?
So experimental design is a bit odd because we're essentially thinking about all future experiments we're going to do. We've not actually got an experiment here. We're thinking about all possible values. So here, we're thinking about all possible simulations that you could ever do. And if I just simulated it, I know the value of theta. So you know, in this case, you know the true value. Okay. So it's a bit of an odd thing to get your head around, but essentially we're maximising all possible experiments we could ever do. Right? We're having to think about that. Think about all possible simulations out there.
But it's sort of like, it's simulations and on top of that is data, it's not just simulations. I mean, the way you do it, you equate data with simulations.
Yes.
There is no error observation,
Yep, no.
something like that. Okay.
So, what do we want to do? We're after the utility of D, right? So you say, well, what's the utility value at time 10? What's the utility value at time 20? Okay? And that's just an expectation, right? This expected value over all possible simulations, all possible data sets, with respect to Y. And so that's just an integral. Okay? So all we're doing here, in order to get this, we're integrating over all possible paths. Right? That's what we're trying to do, trying to get an idea of all possible paths. Okay? But this term here is a bit nasty, this pi y of d. That's the posterior, right? This thing here is the posterior, right? And that's the posterior, that's the likelihood, that's the prior. So in order to integrate over all these possible paths, we're going to have to calculate the posterior for all these possible paths, which is painful, right? We're going to have to solve the inverse problem. Okay? And we have to make a decision at the end of this, right? You know, at the end of this we have to say, this is the best. We're wanting a point estimate, which is a bit odd, we just want a point estimate. And what we're going to do is take the maximum value of this utility function. So we've got a utility function and wanted to find the maximum value, and that's going to be my optimal design, because I have to do one thing. Okay. And U of D, would you believe, is typically not analytically tractable. You know, you're integrating over a posterior. You know, how often is the posterior analytically tractable? Stick another sort of layer of nonsense on top, things don't go well. So it's a strategy proposed by Muller. Okay. And here's a general algorithm. Right? So in line 1, we initialize some design. We pick a set of time points, time 10, 20, 30. We simulate, so this is going to be a stochastic realization, that's Y. Okay. And then we calculate our utility function. So that could be 1 over the posterior variance. So that's our initialized. And then we've got n iterations, and each iteration we propose a new set of design points. Okay. We simulate a new design, a new realization, and calculate the utility function for that realization. Okay. And then we've got an MCMC step, a probability testing step, where we decide which one's the best. So we're trying to move in the general direction of where U is maximized. Okay? So we initialize, and then we're just trying to sort of climb up the top of the hill. Okay? And that's fine. And you run make n large enough, it's guaranteed to find the true posterior, we're guaranteed to get D star, everybody's happy. Except it doesn't really work particularly well in practice, that's the downside. In theory it's perfect, in practice it's just hopeless. So here's a simple depth model, right? So a single parameter, right? Straightforward decay. Okay? So we're starting off with population size 50, and I think here I set the decay parameter to be 1. Right? So if we were allowed to observe 1 point in this line, where would it be? Well, we can calculate the correct optimal design to be 1.61. So you'd make your design, your observation here. Right? That would be the, sort of the best place to make the optimal design, according to 1 over the posterior variance. So we can calculate the utility function, so that's U of D, that's what it looks like. Yep.
You know why 1.6?
Because that's what maximizes the utility function.
Yeah, but why? Where is it? What determines the value of this 1.6?
The slope.
I mean, yeah, the slope is 1, but why 1.6? Why not 1.2? 1.3?
Well, you've got your utility.
Okay, but does it have some meaning?
So, intuition. So the intuition for me would be, if you look here, that's essentially the most separation you've got between all these different curves. You know, so if you chose your optimal design point up here, well, you can't really tell different parameters away very easily. If you chose it down here, everything's dead. You don't learn very
I mean,
much.
does this value have some more deeper meaning, or is it just, I don't know, 1.6?
It's presumably related to the exponential decay of that particular process.
Yeah, there's not a nice, well, yeah. We're integrating over so many things.
Yeah, the exponential decay is 1. Okay, so but why not 1.6 and not 1.7, 1.5?
If you change the utility, you get a different value. So Costas would say, well, suggested, what about the mean squared error? Then you get a different value for the mean squared error.
I mean, the only parameter in your model is this 1, no? So what else?
That's the only parameter. Well, you've got your prior as well, which I've not told you about, but there's a prior kicking a bit behind it.
But basically, I mean, could you kind of, I guess what Jürgen tries to get at, could you, I mean, could you try, I mean, this is a kind of a very simple model where everything kind of decays linearly. So if you were to look at the exponential at that time and check the derivative, is it kind of the maximum derivative, minimum
So I
derivative?
spent the last day doing that. If you were to sum up, if you were to flip this curve around and almost have the cumulative number of events, that's sort of 50% midway between the cumulative number of events. Sort of, you know, here we've had 25 events, here we've had 25 events, you know, it's smack bang in the middle. Well, more, not smack bang, more or less in the middle. You know, so at 1.61, essentially 25 things have died, 25 things have still to die. You know, you're trying to get in the middle. That's, but it's not exactly that, it's just round about that.
So is it exponential of minus 1.61, like 1 over 2 or something like that? Anyway, it doesn't matter.
Yeah. So this is a utility function. That's a thing that we're trying to find the maximum of. And it doesn't look too bad. Okay? The value 100 here is essentially 1 over the prior variance. Right? You know, so the intuition there would be that if you observe the process at time 0.0001, nothing's really changed. So your posterior is your prior, and so that's what this 100 is. It's 1 over the prior variance. Okay? And it doesn't look too bad. Unfortunately, the scale here is a bit of a pain, right? Because if you sort of pretend that this is a probability distribution and normalise this curve, that's what you've got. Right? So if you normalise that curve so the areas under this curve is 1, and sort of pretend it's a probability, so that's what the MCMC is doing, we're getting a distribution at the end, then you can see that the difference between this blue line and a uniform isn't particularly much. You know, they're fairly similar, right? You know, how many things would you have to sample from this blue line in order to estimate the mode? Probably quite a lot. And if you do a sort of a QQ plot, or the cumulative density, so that red line, that's a uniform, you know, it's times increasing, we've got a constant rate of this probability, that's the blue line, and you can see it's not particularly different. If we plot a normal density in this curve, what would happen is it would go along, you get a big bump, and then it'll just plateau. You know, the normal gets most of its mass fairly quickly, depending on the standard deviation. So the trouble with these utility functions are they're flat, right? They're a bit of a pain, they're flat. Which makes MCMC algorithm wander up and down this design space trying to find this mode. Right? So it's going to try and wander up. So the next approach that people thought about, again, it was this chap Miller, was, well, we're going to target something slightly different. Okay? So we're going to augment the state space. Right? And what he thought about doing was, well, rather than going just for U of D, raise U of D to the power J. Right? So we're going to raise this density to the power J. Now if you picture a density in your mind and raise it to a power, what happens? Well, you get the mode and you just sort of pinch it up. Right? So that's when J is 1, when J is 2, you're sort of pinching it up, and when you raise that thing to a power, say 100, you've got the mode, more or less the point mass of the mode, and everything else is going down to 0. Right? So what we're going to do is raise these utility functions to a power, and that's just got the idea of you pick it at the top, and then you're sort of pulling it up, and so you're giving more weight, more power to the mode, because that's what you care about. Okay? But there's a bit of a problem there. Well, if you suddenly raise this to the power 100, you're getting all your mass just at the mode, And so trying to find that optimal design is going to be a pain, right? Because you've now just got essentially a point mass. If you make J too small, then you're back to this horrible situation and everything's flat. And you're wandering around forever trying to find the mode. And so the pragmatic thing is you try different values of J. You know, so you start off with J as 1, have a little play about, start off with J as 2, have a little play about, do it that way. So this is the new algorithm, and essentially at each step now, or each simulation step, we're going to simulate J realizations, right? So previously we just simulated 1, now we're going to simulate J of these things, right? And then we're going to calculate the utility function for J of these things, right? So this one step here, we solved the inverse problem, this parameter inference problem, J times. So to run this algorithm n times, we're going to have to solve the inverse problem J times n. Right? So if n was 20,000, J was 10, we're now solving the parameter inference problem 200,000 times. That makes people cry, right? It's not good. Okay? Again, this all works perfect in practice. You know, it's wonderful. You know, it's just, you know, in theory, you'll hit it, but you might just, well, lose the will to live trying to wait for it to get there. And so, you know, if J is too big, you risk getting stuck in the local minima. If J is too small, you risk wandering around this flat, barren landscape forever. And typically what we do is we run J for 1, 2, 3, or maybe in powers of 2, J try 1, 2, 4, 8, 16, 32, to get an idea of what's happening. But that's not very efficient, right? Remember, we're solving the inverse problem over and over again. Okay? There's a particle approach in JASA in 2006, and the idea behind that is that, well, let's suppose we run this algorithm for J is 1. We've now got a rough idea of what U of D looks like, right? It's not very good, it's pretty awful, but we've got some information. And so we could use that as a proposal for the next step. And then we run it for a different value of J. And then we take a step back and think, well, this is a best estimate for U of D, not that great, but we could use it as a proposal for the next step. Right? We use the information. So it works better in theory. In practice, it's still not great. Lots of nice mathematics, it shows it converges. Lacking in examples, it shows it works. So, quick switch here. These two plots are showing, you know, this one here is the cost of RAM over the last 3 decades. Okay? And these are in the log scales. So in 1980, the cost of for a gigabyte of RAM would make you cry. Right? The cost for a gigabyte of RAM now is getting pretty cheap. Right? It's almost, what's a 4 gigabyte laptop? Everyone's got a 4 gigabyte laptop. 16 gigabyte? That's not that fancy at all. You can go onto Amazon on the cloud, and you can get about 300 gigabytes for £1 an hour. That's how much this stuff's costing you to run a computer. The clock speed, well, something about odds happened here was, well, we had this nice increase. I did my PhD round about then. So that was great. Every time a new computer came out, everybody rushed and fought for this new computer because things just went faster. And then round about 2000, things plateaued, and we didn't get, new computers don't go much faster. Right. And what's happening here is we went parallel, basically. Physics got in the way, we couldn't make these things go faster, so chip manufacturers went parallel. So we've got memories getting cheap, things are getting parallel. Can we exploit this? So, let's have a step back. So when, I don't know if you ever have to do any statistical consultancy and someone comes into your office and they ask you how to do a t-test, and you try to sort of get out from them, what do you actually want to show? What's your problem? Well, if we take a step back, let's think, what do we actually want? Okay. So this utility function is computationally expensive, right? It's horrendous, it's awful, right? It's just not good. Okay. And we've got a fixed computational budget, right? We might be able to calculate this thing 1,000 times or 10,000 times, but there's a we just can't keep running it and hoping for the best, right? Doesn't work. We don't actually care about U of D of Y, right? We don't care about the particular utility function for any particular simulation, right? You just don't. What we care about is U of D. You're not interested in the utility function for any particular realization. You're only interested in the utility function for at the particular design point. And in fact, we don't even care about that. We only care about the mode. Right, that's all we want. It'd be nice having posteriors and distributions and uncertainty, but we just care about the mode. Right? Another thing is, the design space is discrete. It's not essential, but you know, you have to make an observation. Well, by all means, you can give someone time 1 at 15, you know, and specify to the nearest nanosecond. But actually, think about it in terms of aphids. It's, you know, day 1, day 2, day 3, day 4. It's discrete. Might be to the nearest 0.1 of a second, but it's discrete. Not essential, but it helps. So, here's a proposed algorithm. And this is a lot simpler, right? So what's happening here? We're going to have this idea of going through different values of j, right? So we start off with 1, then go to 2, then 4, 6, 8, or whatever, okay? So this is just for a particular value of j, right? Particular power that we're raising it to, okay? And what we do is we propose a design point, and we propose a design point from this distribution here. What does that distribution look like? That distribution is our estimate that we got from the last time we ran, right? So we're on j is 2, well, we've already run this algorithm for j is 1. We've got a particle representation, a discrete representation of what we think U of t looks like, and so we can make clever proposals based on that, right? It doesn't have to be particularly good, right? It's just a proposal. We're going to correct for the fact that it's a bit ropey in a minute. Right? So we've already run our algorithm, might have only been for a limited amount of time. We've now got a rough idea of what's happening, it can be very, very rough, and we're going to use that to propose the future points. We're then going, this step, well, shouldn't be step 2, this step here, it's just going to wiggle that point, right? So I've picked a point I've previously used and then wiggled it, okay, just to try and get the local area. I'm simulating a particular realization. I'm calculating the utility function based on that realization. Okay. And then I'm updating this thing here. What's this? This is my estimate of U of d, right? And all it's doing is just working at the weighted average. So that's my new estimate of U of d of y plus this previous value that I've got from all the other times. Okay. So all it's doing is just a weighted average of, I calculate the utility function at U of d, I keep track of that. I never throw away a value. U of d is precious, right? Someone's cried over getting that value. Okay. So this thing here, U of d is just my estimate I just got, and then I'm just adding it to the previous estimate. I'm just doing a constant update. Okay. And this is just being reweighted by how many times I've calculated this previous value. Okay. So let's have a look. Some more examples. So back to depth model, and what we're going to do is have the same computational budget for all the algorithms I'm going to compare, right? So all algorithms have 24,000 utility evaluations at their disposal, right? And we're going to run each scheme 300 times, and then examine how well it recovers this D star, right? So in theory, all these algorithms I'm going to go through will hit the true value, right? You run them long enough, they will get there in the end, right? But we don't have until the end. We've got until we get to 24,000 utility evaluations. Okay. And in this scheme here, the one I just talked about, we're going to use a sort of adaptive way of choosing GM. Right? So before I just said, well, you start off with 1, and then you might try 2, then you might try 4. Well, why would you might try? You've got an idea of what U of t looks like. And so all this thing here is doing is just getting the variance to shrink by a constant factor. So it's a sort of an ad hoc way of just trying to choose the next J. So here we've got four lines. The black line, so on the x-axis we've got design, okay? So the best value is this magical 1.61, and this is what all the algorithms should get to. Right? Run each algorithm 300 times, and then I plotted a density of the optimal design, of the design they suggested. Okay? So the black line is the one I just mentioned, the new one, and you see that most of the time we're getting smack bang in 1.61, and we're getting a little bit of spread. You know, sometimes it suggests 1.5, other times it suggests a bit bigger. For the Muller scheme, with different values of J's 1, 8, and 16, we're getting these three curves here. right? So j equals 8 is the best, but it's still not that great. J is 1, it's suggesting anywhere from 1 to 2.5, and when j is 16, sometimes it does really well and sometimes it just gets stuck, right? When j is 16, you're powering this distribution up to the power 16, so it's quite, a lot of the space is flat, 0. This is this particle approach in the Jansen paper a few years ago, and again, the black line's ours, and these two curves are from this new particle approach, and sometimes it works well, and other times it's not so great. Okay, so, and then the parameter that we have to choose is how we distribute our utility function evaluations. Okay, I've got 24,000 evaluations at my disposal. Okay, I'm going to have 5 J's. 1, 2, 3. How many utility functions evaluations should I put for each of those components? Should I split them equally? So 4,800 over here, then 4,800 over here, then 4,800 over here. Or I could start off with, well, the first time I run this algorithm, I could have 12,000, and then I might have 6,000, then 3,000, and so on, decreasing. Or I could start off with, well, I'll initially start off with only a couple of thousand and then ramp it up towards the end. And what this is trying to show is, well, one of these is better than others, but actually they're all pretty good. Right? I suspect this is dependent on your particular model, but it doesn't really matter which way you go. You can go decreasing, or increasing, or just keeping them constant. It's all pretty much the same.
So the G values, so it's adaptive in the algorithm. It's always increasing. Or
Yep.
decreasing?
It's always increasing.
Always increasing.
Yep. So why is it going so well? Right? It's essentially, it's never ever discarding a value of u of d. So in the Muller algorithm and in this particle filter algorithm in the Jansen paper, there's a standard Metropolis-Hastings step. You propose a u star and then you accept or reject it. Right? And if you just think about it, you've just spent a long time calculating this posterior value, and then you throw it in the bin. And that just seems wrong. If you just spent 10 minutes, an hour, to calculate this iteration, and you think, no, I don't want it. That's not good. What this algorithm, our algorithm does, is it's exploiting memory. It's essentially just trying to store all possible values you've ever used, all values you've used, and then just keep this running total. Right? Because we're not trying to calculate it u of d of y, we're only interested in u of d. The dimension of d is quite small, right? Where we observe the process. And so what happens is, at j is 1, okay, we've got u of d on the y-axis, and then this is how many times we've estimated a particular design point. So each of these points corresponds to a design point, a d, 1, 1.5, 1.6. And so what this is showing is because j is quite flat, we essentially get a uniform scatter across the density. So we're only ever getting one value at particular points. When we ramp up j is 16, well, we've now sort of focused in, trying to focus in the mode, and some of the points have now been sampled 20 times. So we've came back to that same design point. So this point here represents a value of d, right? Hopefully it's 1.61 or nearabouts, and it's been evaluated 20 times. And so we're getting a better estimate of what u of d actually is. And if you notice here that the maximum here is 250, but now it's been pulled down to around about 180. It's just we're getting lots of variation, and because we're averaging, we're squashing all to the mean.
And the number of points, this is in this example, the number of points in here and there and there and there are the same, 4,800 or
more or less.
okay.
Yeah. A bit more, gradually increasing, but here there'll be 4,800. Here there'll be probably around about 6,000 because you've got that wiggle.
Okay.
Okay. And so here, by the time we get into this point, j is 98. This value's been sampled 120 times, so we're getting really precise estimates on what's going on. Right. The algorithm we've just proposed scales with cores. Right? That's probably not obvious from the start. But the trouble with the Muller algorithm is if we've got n iterations, it essentially scales to n. Right? That's order n times, regardless of the number of cores. Right? So we could have 100 cores available, but the Muller algorithm's zero. You propose a u, you accept or reject. 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 Right? It's hard to make that run in parallel. stuck. What this step here is doing is, because we're constantly keeping track of this u of d, well, we could propose a whole bunch of d stars, right? So we could propose 100 of these things, calculate them all in parallel, and then just keep updating our running track of u of d. If you give me 1,000 cores, then I'll just sample a whole bunch of d's, 1,000 d's. I'll calculate u of d 1,000 times in parallel, and then just throw them back up into my running total of what u of d is. So our algorithm essentially scales the number of j's. So if we've got 5 j's, we're going to plateau at 5, which is quite good. So that's, more cores, the better. We can make use of that. Whereas these other ones here, you're stuck. Last example. So this is the cotton aphid example. So there's 2 species in this particular example. N is the number of cotton aphids. So we start off low, reaches about 1,000, and then dies off at about 50. There's also this other species, or this sort of pseudo-species C, and that's the cumulative number of aphids that have ever lived. Right? So the idea being that when aphids go to a leaf, they're a bit fussy about who lived in that leaf in the past. Okay, so if lots of people have been living in that leaf, they're not that keen and they move on, they emigrate. Okay? So you've got this C, which is the cumulative number of aphids that ever lived on a particular leaf, and aphids don't like other aphids being there. Right? So this thing here essentially feeds into the death rate. Right? So as time increases, this has to increase. Death or emigration becomes more likely, and so they move away. Okay. And even just solving one of these inverse problems isn't trivial, right? To solve the utility function just once requires solving 10 to the 5 ODEs 10 to the 5 times, right? For just one evaluation of this algorithm. And you can optimize that quite well, but you can't get away from the fact that you're solving a set of ODEs 10 to the 5 times. It's just never going to be friendly. And that's a single iteration. But this algorithm scales, right? We're exploiting memory because we're just going to store passive evaluations. So we've got a shiny big new computer up at Newcastle. It's not that shiny, it's not that new, but it's got 26 compute nodes. So you've got 26 of these boxes. And in each node, you've got 20 cores. Okay? So in parallel computing terms, communicating within a node is cheap. Communicating between nodes is expensive. Okay? That's essentially so there's 2 sort of levels. And all we do is at each of these nodes, we're running the algorithm in parallel 20 times, and then every so often, we just pull all the information together in one big lump. Right? So at any one time, we've got round about 500 cores, each solving the inverse problem, each getting an estimate of u of d, and then every so often just pulling all this information. Okay? And there's a trade-off of how often they should communicate. Basically, it's conditional on how expensive your u of d is. Right? If u of d takes you a day, well, expensive communication's a millisecond, so let's go for it. If u of d takes you half a second, then the communication hits you. So it's just a trade-off between how expensive u of d is and how often you communicate. And we can, well, essentially it works. So at the top, this is a 5 design point, or I suppose 4 design point, and as j is increasing, we're focusing in on, I think it's design point 1, should be around about here. That's design point 4, should be around about here. This is our estimate of u of d, right? So when u of d, when j is 1, it's fairly flat, right? That distribution there looks nothing like u of d, right? It's just a noisy representation. But it's been used as a proposal, it's given us a rough idea of what to think about next. Right? So by going along this, we were gradually focusing in. We're using all the past information. Right? U of d is expensive, we never throw it away. Okay? So we're just gradually focusing in on the true value. And these are the 5 values that we come up with. So we was out at t0, and we essentially got a bit just before the peak, and then these 2 others just after peak. And then this one he's probably trying to capture when things die off, and things go extinct. So, future work. So there's a paper in 2003 that suggested ABC. So ABC is approximate Bayesian computation. And the sort of hand-wavy way of thinking about that is you simulate from your model, you compare your simulation with your data, if they're close, accept the parameters. Right? There's lots of variations in that. And that's great. And essentially what they suggest is, well, before we do this algorithm, we do a whole bunch of simulations and use it as a lookup table. Right? So before we do anything, simulate the process 100,000 times. We've now got a big table of all these simulations, and then we can do ABC fairly quickly because we're just looking up, we're not having to do the simulation problem. And the only problem with that is it doesn't really work. Again, it works in practice and in theory, but when you try it, it doesn't work. So it just about works for the depth model, that massive model with one parameter. You get more or less the right answer. And that requires 100 megabytes of storage, so it just doesn't scale. But big data, well, everybody likes big data, especially if you're trying to sell something. So one idea is, well, Amazon, Google have all these computers floating about in the sky in the cloud. Right? And what we could do is, we could do a whole bunch of these simulations and just throw them somewhere up, floating above us. Right? So we're going to do lots and lots of simulations because storage is cheap. Just let them float in the sky. And then when we need them, we ask for it back, because the overhead of getting them back is less than the overhead of simulating it 1,000,000 times. Okay? And there's something called Apache Spark that makes this process a bit easier. But of course, there's a whole host of other things of, well, these things are floating about in the sky, there's going to be a lag coming down, how do we think about the lag? I just said we'll just store a bunch of simulations. If you've got 100 species, do you really want to store every species at every time? A single simulation could be quite big. So do we want to store summary statistics? There's lots of interesting questions of how to go about this. So last slide. So utility surfaces are flat. Right? You could be an optimist and you could say, well, that just means you can choose your design point anywhere, it doesn't matter. These utility surfaces tend to be flat. And it makes sense trying to gradually home into the correct solution. You start off flat and you zoom in. Okay? And evaluating this utility, this inverse problem, is noisy, expensive, painful, and we don't ever want to throw away U of D. Right? That's just silly. And so what we've proposed is this exploiting memory in order to store all previous values of U of D, and then it also scales with numbers of cores. Thank you.
I know that you were purposely sort of avoiding talking about how you're actually solving the inverse problem, but I'm interested in seeing.
Oh, right.
So you said at one point that you did 10 to the 5
right.
iterations.
Yeah.
So I was wondering, is this MCMC?
Okay. So
What algorithm are you using, and how
Yeah.
good is your convergence within that number of iterations?
So for the first model, the polyQ model, that was horrendous. And so what we did was we fitted a Gaussian process to a whole bunch of simulations, and then the MCMC algorithm for evaluating the posterior is actually running a Gaussian process emulator. For the aphid, we're using moment closure, so that's why I'm suddenly switched to ODEs, because I hope no one will notice. So we've represented this model as using the linear moment closure approximation, and that means we've got a bunch of ODEs, some for the mean, some for the variance, and that makes it easier. In terms of, well, at each iteration we're solving this inverse problem. Have we done it well? That's a hard thing, because when you're doing MCMC, you've got all this idea about, well, you check for autocorrelation, you check for Bonin, you check for this and this and this. But if you've got that within your MCMC, MCMC within MCMC, you can't go and check all that. But there's one small thing: we simulated the data, right? We know the price, and if you've simulated the data, well, you know good starting values for it to kick off, because you've simulated that thing. And also, even though you've got all these different realizations, the posterior is not actually that different. So just doing a bit of pre-simulation, you can work out the posterior, and then for these things I've used an independence sampler, and I'm getting acceptance rates of around about 90%. Because utility function is flat. Why is the utility function flat? The posteriors are all the same, more or less. The posteriors are all the same, and you can use that as a proposal. Initially I tried all sorts of funny nonsense, Riemannian manifold, then I realised an independence sampler is better.
of simulated annealing? It seems your method, like raising the power,
Yes.
simulating annealing, you try to find the exponential of u over epsilon.
Yeah.
So it will be kind of similar.
Yes, it's kind of similar to the annealing. Yes, so there's definitely similarities. Similar to the annealing, you still get the same posterior, whereas what this is doing is we're actually changing the target. So when j is increasing, we're no longer targeting u of d, we're targeting u of d to the power j. So there are similarities.
So in simulating annealing, you don't target u, you target exponential of u over epsilon. And the epsilon is kind of the j for you. But you can decrease epsilon so that it decreases g.
Yeah.
And both concentrated into. I don't know, it seems similar.
Yeah, no, yeah.
So, I mean, can I ask something that will perhaps be a bit naive? So, you mentioned that, and I kind of understand that, calculating this u is expensive and you don't want to get rid of that. So, is that some sort of generic principle? So, I mean, so in a normal kind of, if you like, let's say like that calculating your likelihood would be expensive, yeah? So for an inverse problem, but not with sort of like two levels of MCMC like you have here, just one level.
You're just wanting to calculate the posterior.
Yes. So would that sort of approach kind of still apply to that? Sort of like try not because there you kind of accept or reject and you even in the independent sampler or even in sort of like, I don't know, something like Mala or something like that, would it make sense to try to do some particle thing on top of that? Or
So the reason why we don't tend to do this with standard MCMC problems is that D is discrete, right? So somewhere on my code, I've got a very big matrix with all the different values of D that I've tried. Right? So I've got D is 1, 1.1, 1.2, 1.3, 1.4. Now because it's discrete, I can store all these different U of Ds. If I was interested in, say, theta, well, that's continuous, and you've now, how do you store that? You've got continuous value, and you then go down to particle filters and trying to represent continuous distributions.
but could you just pretend that it's discrete? I mean,
Well, that's what particle filters do. You've got a continuous distribution, you represent it with a bunch of points, and then, as you can imagine, well, how many points do you need? What happens if the dimension increases? Everything just dies a horrible death.
Any other questions? No. If not, let's thank Colin again. It does get better.